Okay, so that's two symmetries that we've talked about. We've talked about, two. We talked about a cylindrical Gaussian surface. That was a cylinder. We talked about the Gaussian surface that was a pillbox. And now what is the last that's left? So we got this one check. We got this one check. And now we have to worry about cylinders. Now, when I talk about cylinders, I want to do two different kinds of cylinders. So let's talk spheres. I want to do empty. This is also called a spherical shell. In case you see it and you're like, oh, I've never seen this before. Yes, you have. Okay, so what does a spherical shell look like? And it's empty. Let's suppose it has a radius r. Pick a charge. What charge do you want on it? Plus. Okay. Now I want you to split this problem into two things. Inside and outside. So let's do our Gaussian surfaces. So let's suppose I make my Gaussian surface here for the inside. What is the E field on this Gaussian surface, say at a radius A, B? I don't know, pick one. So at R equals B, inside, what is the E field? Good job, Nick. What would it be?
0.
0. Because the charge resides on the surface only. So the E equals 0 inside the shell. Why? Because it's hollow, right? And the charge only rests on the outside, on the surface, right? Now, on the other hand, when I want to make my Gaussian surface outside, let's say of radius, I don't know, A, how will I do this? That can't be 0, can it? Nope. So what do? First of all, I have to write my Gauss's law. This is a spherical surface. So I should be using my spherical charge density. So my Q will become sigma A divided by epsilon naught. Agreed? And this A is the charge that's enclosed. And this A defines my Gaussian surface. So how will I draw the left-hand side? E R sine theta d theta d phi equal sigma 4 pi r squared divided by epsilon naught. Just pause for a second. Make sure you understand this. Note this area uses up the radius of the shell itself, right? The shell radius is capital R. Whereas the Gaussian surface R is A. So on my left-hand side, what will this become? E A squared 2 pi times 2. Let me finish writing this and then I'll let you look at it. Do you see the difference between the two? One, you're defining it for your Gaussian surface, which is on the left side. And the other one is getting defined by whatever charge is enclosed in that surface. So be very, very careful when you do this. Okay, so once that is done, so that gets canceled. And what am I left with? E equals sigma R squared divided by sigma naught A squared. And in order to convert it into a vector, I will multiply it with A hat. Because the Gaussian surface is defined as R equals A. So it will be the normal to the Gaussian surface. So remember, the left-hand side defines the Gaussian surface. The right-hand side defines the charge enclosed. Good? Bobbleheads? Okay, excellent.